Okay, class, I got a request for another one here, number 26. So here, let me talk this one through. It says here, a ball is fired vertically upward at a speed of 30 meters per second. So maybe I'll kind of make a picture of a ball, kind of pointing upward, and that's its initial speed, 30 meters per second. It says construct a table showing the height of the ball and its velocity at the end of each second until just before the ball hits the ground. All right, so if I make this little table, this will be time, and so we'll go 0 seconds, 1, 2, 3, and it'll take some practice before you begin to realize that this would take 6 seconds. So I'm just going to make a table with 6 seconds only because from experience I know that, but we should just, start counting through here. And if the first part of this table is then the velocity, and I should put time in seconds and velocity in meters per second. And then velocity here is, of course, the speed of it, and it very clearly says that when you initially start it, so at 0 time, it's 30 on its way up. And an important lesson of this chapter was that the acceleration because of gravity, which we give a symbol of g, is 9.8 meters per second squared, or approximately 10. So let me just work with 10. This is what I did in the video lecture. And it's just a nice number. It really just means I don't have to grab my calculator and do some fancy calculations. And it gives me a chance to focus on thinking about the physics than to worry about the mathematics. But I hope what you got out of the chapter, besides the fact that everything has an acceleration of 10, the acceleration is downward at 10. Because another part of this chapter was that if something is moving, so I'll put velocity, in the same direction as its acceleration, that means it goes faster. But another case is when it's moving in one direction, and I'll just list to the right, but the acceleration is to the left, that makes it go slower. And so these are our two options. So the acceleration due to gravity for any object, and whether it's going up or down, and whether it's a big object or a small object, or whether it's a blue or a brown object, or whether it's done on a Monday or a Tuesday, none of that matters. It's just this is always the acceleration. It's always 10, and it's 10 downward. So if you throw it upward, it would be a scenario like this, where it is going up, but the acceleration is down, and that means it goes slower by 10. So that means 1 second later, it has slowed down to 20. Now, it's still going up, and so it would be maybe here in my picture, and so it's still going up. But see, it has changed by 10. A second after that, it has changed by 10 again. But it's kind of the same scenario. It's going up, and the acceleration is down. So we are slowing down by 10. It's always a change of 10. I didn't do a very good picture here. Maybe I'll put it above here. And so there's 10. Now, a second after that, it has come to a stop finally, a speed of 0. And so that's its maximum height. So finally, we get to a velocity of 0, and that's 3. Which, by the way, that's how I knew it was going to be 6 seconds, because I saw the 30, and realizing I was going to be taking away 10, it would have come to a stop in 3 seconds, and everything's going to repeat in reverse as it goes down, so it'll be another 3. And so in case you were wondering, that's how I knew from experience that this was going to take 6 seconds. All right, so far I've concluded that it would take 3 seconds before it comes to a stop, and now it begins to fall back down. And so again, the acceleration is down at 10. But this time we have something that looks like this. That is, we are moving downward and we are accelerating downward. And they're in the same direction, so it starts to go faster on the way down. And so it always changes by 10. So a second later, it's going to be going 10. And a second later, it goes and increases by another 10. So that's up to 20. And then it changes by another 10. And so it's to 30. So please remember what acceleration is. And that's, again, the point of this lesson is acceleration is a change in the velocity. So when you say something has an acceleration of 10, I like to write it this way as 10 meters per second each second. instead, and that's a compound fraction. So mathematicians like this, but writing it as 10 meters per second each second can be very useful. It gives you an understanding of what is meant by the math. Change by 10 meters per second each second. Okay, so I did. I'll say it again. I started with 30 and I changed it by 10, changed by 10, changed by 10. But in this case, since they're opposite, the changing by 10 is a decrease. Then on the way down, since they're in the same direction, we're going to change by 10 again, but it's going to go up. So 0, 10, 20, 30. So it basically hits the ground right here going downward at 30. In other words, it just repeats itself. It gets to the top and it gets down here. It's going 10 down. It gets right here and now it's going 20 down, 20 and 10. And that's probably the easier of the two. Let's then put the height. That's the second part. And I would presume that what they mean by height is the height from, where it started. They said it's thrown up. And so if you really throw something, this is, probably measured from the palm of your hand. The ground might be a little bit lower than that. But I think they, don't want us to say the height above the ground because we really don't know how high the person is who's throwing it. Or it says fired, so we don't know how big the cannon is. But let's measure then maybe I'll just take it as a little cannon here. Let's measure the height from the edge of the cannon. So it leaves the cannon at 30 and then, slows down and speeds up. So the height will be measured from the edge of the cannon. And so, of course, the first one is 0. It's got a height of 0 right as it leaves the cannon. Now, the next one, here's where it gets a little bit harder, is how high is it after 1 second? And so, remember, distance equals to average speed multiplied by time. So, when I look at these two speeds, I need to average them. So, it comes out at 30 and then begins to decrease. 30, 29, 28, 27, 26, 25, 24. And it gets eventually down to 20. And so if you average these two numbers, so 30 plus 20 divided by 2, right? That's the average of two numbers. You add them together, divide by 2. That's 50 divided by 2, and it's 25, which it makes sense. It's right in the middle of those two. It's right in between the 30 and the 20. So its average speed is 25, and it's sort of like it traveled at a rate of 25 for that 1 second. So there's the average speed, 25 for 1 second means it would have gone 25. So that's how we get the height. We look at the average speed, not the instantaneous, because we wouldn't want to use the 30 because it didn't travel at this rate of 30 for the 1 whole second. It also didn't travel at the slower rate of 20 for the 1 second. And so sometimes it was above the average at 25, and sometimes it was below the average. And so that's why we want to make sure we put here the formula for the average speed. That's why the bar is there. All right, well, we can keep doing this. We can either look at the whole 2 seconds or just the next 1 second, so between 1 and 2. And I'll just do that. Let's look at between 1 and 2. And maybe I'll put the same little formula here. Okay, so between this 1 and 2, it looks like it is averaging 15. See, it's at a 20 and then slows down to a 10. So halfway between is a 15. I'll do the math right here. Here's a 20, here's a 10, add them together, divide by 2. All right, so that's a 30 divided by 2 is 15. So for the next 1 second, it's equivalent of going 15 for that whole 1 second, which means it would go 15. Now, it didn't really go 15 for the whole second. But again, for this time frame between 1 and 2 seconds, you don't want to use the 20 because it didn't go at a speed of 20 for the whole 1 second. In fact, at the end of it, it was only going 10. That's why we use the 15. It's right in the middle. Sometimes it's going more than 15, and an equal amount, it's going below 15. Okay? And so that's why the 15. So it's going to go up another 15. So between 1 and 2, it goes 15. Now, it's already at 25 above the cannon. So if it goes up another 15, I'll just put it here on the side, add 15. That becomes, what, 40. And let me just play the game all the way down. The average speed between the 2 and 3 seconds is 5. So that means it's going to go another 5. That's already 40, so we're going to get 45. Of course, now it begins to go down. But again, I can just kind of look. Between 3 and 4, it had an average speed of 5 going down, so it would travel 5. It would go 5 down. So it was already a maximum of 45, so 5 down would be 40. Same game here. Between the 4 and the 5 seconds, I'd have an average speed of 15. Okay, so that means it's going to go 15. It would be that same formula. Distance equals average speed times time. So I need to subtract off 15. Maybe I should have put add 5 here, minus 5. Okay, so if I subtract off 15, I'm down to 25. In fact, you can see it's in reverse. I told you it was going to be in reverse. And then finally, the average speed between 5 and 6 seconds is 25. So it's going to lose 25. So if I subtract 25 from its current height of 25, we get back to the height of the cannon. And so it's not a surprise that, you know, everything is in reverse. It goes up, 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 up to a top, down, down, down. And so the rate at which it is slowing down is also the rate at which it speeds up. So it's not a surprise that these numbers from 0 to 3 mirror 3 to 6. They're identical. All right. Hopefully that helps.